In this lecture, we start our discussion on finite wing geometry and flow features around a finite wing. Let us ask two basic questions and answer them before we begin the discussion. So, the first question is, how is the geometry of a finite wing different from an infinite wing or airfoil, on which we spent time during the last several lectures? The answer to this question is that finite wing is a 3-dimensional body, while the airfoil was a 2-dimensional one, with its span moving to plus minus infinity. And because it is a 3-dimensional body, it has a finite span. So, in the span-wise direction, there are ends to this body. What is the second question? How are the aerodynamic characteristics of a finite wing different from its airfoil section? The answer to that is, there is a component of flow on the finite wing in the span-wise direction, which was not there in the case of airfoil, and therefore, everything could be considered in a 2-dimensional sense. So, what do we mean by the span-wise flow? If we were to take an airfoil section and stretch it in the span-wise direction. So, following right hand rule, the positive z axis will be this way. So, you are basically spanning it towards negative z axis. Then in a finite wing, there will be a component of velocity along z. So, if I call that component of velocity as w, then w is not equal to 0 in the case of a finite wing, while w is equal to 0 in the case of an airfoil. And that is why we can solve for the flow field by just looking at u and v in the case of an airfoil, while you need to look at u, v, w all components in the case of a finite wing. So, an airfoil is a section of a wing with theoretically infinite span. Therefore, there is no effect of span-wise flow on its characteristics. When does the span-wise flow work at all or occur at all? When the body has finite ends, finite span. This is something that we have to set firmly in our minds. So, in an airfoil, consequently, because there is no span-wise flow, there is a 2-dimensionality. Now, going back to the wind tunnel test section, what would it mean when we try to do some experiments? The other day, we had drawn an airfoil model which spanned from one side wall to another. So, this is a side wall, this is another, this is the top, and the other one the bottom wall of the wind tunnel. There is a flow coming from the upstream direction with an average velocity of u infinity and coming and meeting this airfoil section, which is stretched end to end of the two side walls. So, when the flow moves past it, it does not find any ends, while if you decrease the span and you put in a model like this, where these ends are not reaching up to the side walls, then the flow sees a body with finite span. This is the implication of having an infinite span or finite span in the wind tunnel test section sense. Let us look at some of the more detailed features of what is going on when you have a finite span. So, this is a finite span wing. These are the tips of the wing, we say wing tip, the flow is approaching from that direction, and there is formation of so called wing tip vortices when such a flow occurs. Why is it so? There is a pressure difference between the lower and upper surfaces of the wing. We learnt it in the sense of an airfoil, but here we are talking about the wing because we have a finite span. So, there would be pressure difference across the lower and upper surfaces of the wing as well. So, if there is higher pressure below the bottom surface, has higher pressure compared to the top surface which has lower pressure, it is good for the wing because that would lead to lift generation. But as a byproduct, the high pressure air tends to leak from the bottom surface and tends to move upwards at the tips. So, the flow curls up at the wing tips. Why is it? It is purely because of the pressure difference. What is the flow trying to do? It is trying to run away from the high pressure to the low pressure zone. That is the direction in which nature on its own would proceed. And as a consequence, there is a curling up of the flow. Remember that the flow is moving with respect to the wing, and therefore, as the flow curls up, it actually has a rotational character associated with it, which shows up in the form of a tip vortex, and that tip vortex gets transported, gets advected with the free stream. It moves downstream. So, this is basically a trailing vortex which is forming at the two tips of the wings, and therefore, there are a pair of trailing vortices. In the diagram, you can see there is a nice picture of an aircraft flying through some clouds, and it has left behind it in its wake two curled structures which the cloud has taken in its flight path. So, there seems to be a motion like this which is induced due to the movement of the aircraft through the clouds. The downward movement of the flow was what was faced by the wings when it passed through those clouds. This is what is called as a downwash. What was happening beyond the span of the wing was an upward movement, but which did not impinge on the wing. It moved at its periphery beyond the wing tip. That was an upwash. So, upward movement or downward movement induced by those wing tip vortices when they move through the clouds. Let us try to look at some more features here. The tendency of the flow to leak around the wing tip induces a downward velocity component which is called as a downwash, which we just saw in the diagram. What does it create? It creates an induced angle of attack indicated by alpha I. This is that angle. The geometric angle of attack is reduced by this induced angle of attack, producing an effective angle of attack. The effective angle of attack is the one which is visible to the airfoil. So, that comes out to be the geometric angle of attack minus alpha I. Geometric angle of attack is nothing but the angle made between u infinity and the chord of the airfoil, or here we will talk about the section of the finite wing. So, here though you are not able to see the three dimensionality of the finite wing, you can consider this to be a section of the finite wing. But we are just taking into account the effect of the downwash even in the sectional view. The effect is not restricted to the reduction in angle of attack alone. Another effect of downwash is to incline the lift force towards the rear direction by the same angle alpha I. So, earlier the lift force was originally normal to u infinity, that was the original direction, but because of the induced angle effect, the lift vector tilts and tilts backwards. Because of this tilt, a component of the lift force acts along the free stream direction, producing an induced drag. Therefore, the tilting has become a disadvantage now. So, even if the lift magnitude is not very different from what it was before, the fact that it has tilted backwards would give rise additionally to this drag. Of course, there is a disadvantage even because of the reduction of alpha, because you would understand that with reduction in alpha, what essentially happens is that the lift will also reduce. So, there is actually a twofold reduction. The three-dimensional flow induced at wing tips alters the pressure distribution on the wing in such a manner that there is a net pressure imbalance in the free stream direction. And if that happens, you know from your previous experience that increasing net pressure imbalance in the free stream direction causes increasing drag. Therefore, induced drag can be treated as a kind of pressure drag. Let us try to go a little deeper. Let us take another view to explain the things. Let us say we are looking at a transport aircraft from behind, from its rear side. Okay. So, this is a rear view. The aircraft is in flight. Let us say we are looking at the engine exhaust side. This is its tail plane side, etc. Okay. So, the aircraft is actually moving into the plane of the paper. Now, if we watch how the wing tip vortices have propagated downstream in perspective, you would find it would look more like this. And if you try to look at the induced velocity variation by virtue of the wing tip vortices, how does it look like? It looks somewhat like this. So, beyond the wing tip, the velocity points upwards. So, this is what is called as an upwash effect, but that is not experienced by the wing. What is experienced by the wing is the downward movement which is induced by the wing tip vortex which impinges on the wing. Incidentally, the entire wing is experiencing the downward induced velocity, because this is the region which was experienced by the wing, and that contains the downwash effect. Therefore, the physics that we just discussed, that you have an induced angle of attack, there is tilting of the lift force, etc. So, you can say that this is the velocity distribution across the span. Velocity distribution across the span induced by the pair of wing tip vortices. Let us do some more discussion on the finite wing geometry. Let us draw a finite wing which has a rectangular plan form. So, we are now looking at the wing from the top. This is the top view. So, if you were to take a section of the wing, let us say it has an airfoil section that will show up like this. This is the chord length. This is the span of the wing. The planform area would be B into C. How would the flow behave as it moves past the wing? The flow on the top surface would turn this way as it moves past the wing. The flow at the bottom surface would turn the other way. Why is it this way? Remember that it is all due to the effect of the curling up of the flow from bottom to top, that is turning the streamlines. This is typically the mid-span location of the wing, and if you mount this wing on an aircraft fuselage, the fuselage of the aircraft will come somewhere here, and the nose of the aircraft will be upstream. We assume that the flow is moving from top towards the bottom. You could have different planform geometries. In finite wings, the rectangular wing is a straight wing. There could be another possible geometry like this and others too, which belong to the same category, that is straight wings. It will become clearer to you if we include one more detail in these drawings, that what we mean by a straight wing. So, there is something called as the sweep angle, and in this case the sweep angle happens to be 0. So, you have a half chord line drawn over here. This is basically the line, the locus of mid chord points along the wingspan. So, if this locus happens to be a straight line, then it is a straight wing. It is true for the rectangular wing, it is true for this. It is true for an elliptic wing as well. So, these are different planforms. There is a very important term associated with finite wings, which is called as aspect ratio. which is represented as B square by S, B being the span, S being the area. So, the ratio B square by S gives us the aspect ratio. For a rectangular wing, aspect ratio is given by B square by B into C, which is B by C. Higher the ratio B by C, that means higher the wingspan versus the chord ratio, higher is the aspect ratio of the rectangular wing. Higher aspect ratio or higher span basically would make the finite wing have aerodynamic characteristics closer to the airfoil section. Remember that for airfoil section, the aspect ratio is infinity. We talked about straight wings. We could have swept wings which look like this. This is the midspan. This is the locus which we are calling as the half chord line. Also, there is a root chord and a tip chord. This angle is called as, let us mark it as capital lambda. So, capital lambda is the sweep angle. So, if it is non-zero, then we have a swept wing. Here it is sweep back, that means it is swinging back towards the fuselage direction this way. If it was sweeping forward, the angle would have moved the other way. Further, there is something called as the taper ratio, which is given by the ratio of the tip chord to the root chord. That means, the wing is becoming narrower in terms of chord length as you approach the tip. We more often see these kind of swept wings as the free stream velocity increases. Now, let us concentrate on the different types of drags acting on a finite wing and an airfoil section. The total drag on a subsonic finite wing, let us say for simplicity we consider incompressible flow, is the sum of skin friction drag, which is due to shear stress distribution, and pressure drag, which is an imbalance in pressure acting on front and rear portion of the body when flow is separated in the rear, as well as induced drag, which we just learnt about today due to the finite wing tips. So, there are essentially three components of drag which are acting over here. In terms of drag coefficient, we are looking at the skin friction effect, the pressure effect, and an induced drag effect. So, all those effects come into these two estimates of drag, which we will look at after we look at the second point here. The total drag on a subsonic airfoil is the sum of the skin friction drag and the pressure drag. So, we will use these nomenclatures, skin friction and pressure, as dF and dP, while induced drag is 0. It is just because it is an infinite section. So, in this case, if you look at the 2D aerodynamic characteristics, that would be represented by lowercase c d, and it is the sum of the skin friction drag and the pressure drag non-dimensionalized by the product q infinity s. When it goes to the induced drag, it is talking about a finite span body, that means a 3D body, hence we use the uppercase c, and we non-dimensionalize the induced drag by the product of free stream dynamic pressure and wing planform area. So, we have to keep in mind that induced drag is there for a finite wing, it is not there for an airfoil, and for both skin friction drag and pressure drag are present in an incompressible flow or low speed subsonic flows. Flows which occur below a Mach number of 1. Of course, we have not discussed about Mach number in detail yet, but it basically means that we are flying at a speed lower than the speed of sound. The sum of the viscous dominated drags, namely skin friction drag and pressure drag, is often called as profile drag. In high speed flows, starting from high subsonic flows and extending to higher speed regimes like supersonic and hypersonic flows, which we will look at later, there is a drag due to formation of shock waves on the body. That is a very special kind of drag which is going to occur only at high speeds. That is called as wave drag. So, that will be an additional component of drag which will affect a finite or an infinite wing section when it is moving through high speed flows. The total drag on a supersonic finite wing is the sum of profile drag, which means both skin friction and pressure, wave drag as well as induced drag, while the total drag on a supersonic airfoil is the sum of profile drag, skin friction and pressure and wave drag. Induced drag is 0. Mind it that in addition, if you are assuming the flow to be inviscid, which is of course a theoretical situation, because you can never ignore at least the boundary layer effects around the body anyway. So, in a perfect inviscid flow, remember that even the skin friction component will go to 0. So, let us see what we learnt in this lecture. Here we initiated the discussion about a finite wing and its geometry. We briefly looked at the flow features of a finite wing, the wing tip vortices, the induced drag, etc., and how it differs from an infinite wing section, that is an airfoil. Thank you.